complex, and then that complex ends up forming what we call 5 factor 10, or we call X if you want to. 5 factor 10 now acts as an enzyme and causes or activates enzyme prothrombinase and converts prothrombin to thrombin threads. And then thrombin acts on fibrinogen to make fibrin. Fibrin creates these long protein molecules that get stuck inside the hole. As they get stuck inside the hole, they're real sticky and they form a meshwork, and other clotting factors and platelets and blood cells get stuck there. And pretty soon you get this really big clot inside the vessel wall, and the bleeding stops. Are you with me? You do not have to memorize a single step that I did, but in this mechanism, the first step that occurred was something was released. And that molecule had to react with or encourage a second molecule, who reacted with or encouraged a third molecule, who reacted with or encouraged a fourth molecule. And the reason I keep using encouraged, because it's positive. And so, because you have to have all of those steps that have to occur, one after the other, without one helping the other one to occur, the whole mechanism falls apart. Those are called positive feedback mechanisms. And that's Martini's example.
So blood clotting is positive.
Yeah, positive feedback. We have very few positive, just a handful of positive feedback mechanisms. Most of our bodies is usually negative. Have I lost you? Okay, let's do a simple one. Where's the, yeah. So you're all familiar with this one. This is a positive feedback mechanism. So this is the baby. It's been sitting inside of mom's uterus for 9 months. It's like trying to get out. And so he used to sit kind of high. Now he starts dropping down to the bottom of the uterus. When it does, his head pushes on the cervix. And so when the head pushes on the cervix, it sends a nervous signal up to the hypothalamus and talks to the posterior pituitary for release of oxytocin, which goes down to the smooth muscle of the uterus and tells the smooth muscle to contract. So when it pushes on the baby, where's his head go? On the uterus floor. More pressure on the uterus, cervix, causes a greater nervous signal, which goes to the hypothalamus and says, well, let's release even more oxytocin from the posterior pituitary, who goes back and pushes on the baby, so he pushes more on the cervix, which sends a stronger signal from the nervous system to the hypothalamus. You see how this is going to work? This is a positive feedback mechanism. It's never ending. Okay, well, actually, it is. Well, yes, it does eventually, but it takes about 12 years. I have a 21-year at home, so I think it takes 21 years and 9 months before it ever ends. So I don't think he's ever going to leave. I'm just kidding. I should tell you. I am going to talk about my family. I will tease and make fun of my family. They have absolutely no legal privacy rights whatsoever. And so if you can say, well, I'm going to go tell your wife or your kids, and I'm going to go, they've heard that story before. So in fact, one of my kids had to sit through A&P with me while I told all these stories. I know, that was a really bummer. So you see how this works? This thing keeps encouraging you. Now, eventually, does the stimulus go away?
Yes.
Yes, it does. So our goal is to deal with the stimulus, but in this case, we didn't want the stimulus to go away, and we got the baby out, because that was our ultimate goal. Making sense? All right, good. So let's go back, and let's take a look at the next week. Gosh, your fingers, sometimes these words, sometimes.
The sugar is snack you provide enters your digestive system and is broken down to simple sugars like glucose. Glucose enters the bloodstream, causing an increase in blood glucose levels. But various mechanisms bring blood glucose back down to its normal level, the set point. This is an example of homeostasis, the body's tendency to maintain relatively constant internal conditions. Hormones produced by the pancreas regulate blood glucose levels. Let's zoom in. When blood glucose levels are high, glucose molecules leave the blood and enter beta cells in the pancreas. The beta cells respond by releasing the hormone insulin. Insulin enters the bloodstream and is transported to cells all over the body. Let's see what happens in the liver. Insulin binds to receptors on liver cells. This causes the cells to take in more glucose. Inside the liver cells, glucose is converted to glycogen, a storage molecule. Blood glucose levels decrease as glucose is taken up by liver cells and other body cells. As a result, less and less insulin is released by the pancreas, and blood glucose levels stabilize at their set point. This is an example of how negative feedback maintains homeostasis.
So does that make sense, everybody? So you get the idea of homeostasis, and then you just see a negative feedback mechanism. The next one that we're going to do is glucagon, and it's a negative feedback mechanism. It's just the opposite, so we don't have to see that one again. So we've seen how that negative one was going to work. And when we take a look at it once again, the mechanisms and how we regulate things in our body, what we're going to notice is most of the time there will be a negative feedback mechanism. So Martini does a pretty good job of when it is a positive, he tries to tell you this is a positive feedback mechanism, so you'll recognize it. And the rest of them are obviously negative. So what we're trying to do then is we're trying to maintain homeostasis, and we do this by this collection of chemical activities that go on in our body. So that entire collection that goes on is called metabolism. So metabolism is just defined as the sum of all the chemical actions that occur inside the cells of your body. Now, when we think about metabolism, we always think about, I wish I had a high metabolism and not a lower, so that I'd eat 8,000 calories in chocolate every day and I would never gain weight. And so that's not only a bad concept, or even the chocolate stuff, but the idea that it's related to weight. Because what we're really saying is that if we have a high metabolism, what happens to the amount of chemical reactions?
Yes, sure, a lot.
We have more. And when we have more, we need more ATP, and we get ATP by the food that we eat. So you're right, so we're very, very active, and we're working hard, and we have a lot of lean muscle mass and all that kind of stuff. And then our body's working harder, and it's having a higher metabolism, more metabolism, and then we get to eat more calories. Are we okay? So, but from an anatomical point, it is simply all the chemical activities that go on in the body. So what we're doing is we're trying to maintain homeostasis with these chemical activities, and all those organ systems are working together to try to make that happen. So the second theme that we have, so this is in your notes also, is we have this theme that says the part is no greater than the whole, and the whole is no greater than the part. Now, what you're going to find, if you read some books and you hear that in this talk, they'll say the part is no greater than the whole, but the whole is greater than the sum of the parts. That's kind of an axiom that's been made here a long time. But I've kind of tweaked it, because what you guys are going to do primarily in your careers is you are going to go out and treat people who are not in homeostasis. And so if they were in homeostasis, their body would be working just fine, and then they wouldn't be in the doctor's office or the hospital. Does that make sense? Okay, so what I want you to start thinking about is the part is no greater than the whole, but the whole is no greater than the part. If that person comes into the ER and you're on duty and they're having a heart attack, that heart isn't working because it's not working, the rest of the body's not working. Somebody has a stroke and their brain's not working, the rest of the body's not working. Somebody comes in, they had this huge laceration in their leg, they're about to pass out from blood loss, the rest of the body's not working good. So what we'll think of is, we have these great parts, but they have to work together in order for us to maintain homeostasis. And what your kind of job is going to be ultimately is to figure out which part is screwing this up and how do we fix it for this person. Because we want to get back to all the parts are working together to maintain homeostasis. Are we okay? All right. All right, so when you take a look here, what I'm not going to go through this whole chart. This is in your book. You really don't have to memorize any of this. But Martini's trying to do a nice job just kind of showing you that one system really isn't going to be in charge of something. Everything with body temperature, fluid composition, volume, weight, blood pressure, it's always multiple systems that have to work together to help us to maintain that homeostasis. And so you guys did this in lab already, correct? You started learning these parts? Okay, so did Jen talk very much about lab quizzes at all? Sort of? Okay, so lab quizzes cover the material from the previous week, and so your next lab, because Jen's got all my lab quizzes, so she'll probably make them kind of based on those. But you typically don't have much of the wrap on there, but you do have stuff from the first lab in large amounts. So you should expect, when you come in on Monday, there'll be a person that looks like this. Now, on your quiz. Obviously, okay, an interesting class. I stand there with arrows going all over. Make all those parts. So what will happen is it'll be a lot fewer, but you'll want to be able to identify the anatomical landmarks. And so I think we use that pick ones. I think they're pretty straightforward, but just kind of giving you a warning and a heads up that this will show up. On your lab, and I'm real upfront about lab exams to some extent. I can't tell you what's going to be on it, but you could probably guess that it'll be on your first lab exam, and you should guess that it's probably going to have a lot of lines on the first lab exam. So I'm just kind of So I'm not going to go through all these names. What I'm going to do is talk about when you take a look at these guys, and he has Martini's done a much better job in this orange edition than in the past. When we take a look at body regions and stuff, there's a noun and a verb that's associated with those landmarks and regions. So what will happen is sometimes you'll see a line going here and it'll say femur, and you can't use femur for the body region because the region is named for the bone, and the bone is the noun and that's femur, and the region is femoral or femoral. Are you okay? So on this edition, you finally listened to us apparently because he's been wrong for years. On this edition, he's mostly put the regions on here and not the names of the bones. And so you just have to really go through and kind of take a look at these and just sort of learn that. It's just taking anatomy that's memorization and regurgitation kind of stuff. There's no real tricks. Just get the picture out and know that.
If I recall correctly, in the lab book for hand, instead of saying manual, it's like manus, I think.
Yeah, it probably does say manus. And actually,
Doesn't it be common for a lot of them to be slightly different convertible?
yeah, I'm glad you asked that. I was going to say, what you're going to find is we actually did something that we think is a good thing, and sometimes students don't. We have a lab manual that's different than a different author than your textbook. And one of the reasons for that was to get two different sets of pictures for everybody. The other is that they don't all use the naming system, so you're going to see more names than you would if you used the same one. So this can be manual or it can be manus, either one. So what you're going to find is that, and I think Martini described this a little bit if you read that very front stuff in the book, which most people have a tendency to skip, and when I was a student, I did too. I never read that stuff until I became a teacher. I went, hey, there's hints in the front of the book. What happens is we're doing some big name changes in AMP, and they have been for the past 4 or 5 years. So it used to be there were a lot of names that were called honorarium names. So, I discover something, and so we call it the Jim's corpuscle, because I discovered that corpuscle in the skin or something. And so forever, people remember Jim, who discovered the corpuscle. They've decided that honorarium names really aren't that helpful to people, and so they changed the names from honorarium names to names that are more descriptive. And some of them are good changes, and some of them aren't. So in your pancreas, where we're creating insulin and glucagon to help control blood sugar levels, we had there's these little clusters of cells that used to be called the islets of Langerhans.
Now, Langerhans has his name all over AMP because he was like this mad science tissue cellular guy, and he figured out all kinds of stuff. So we see Langerhans this and Langerhans that. Well, they decided that didn't help anybody. So they now call that the pancreatic islets. Well, that makes a lot of sense. They're in the pancreas, and when you look at them, they look like little islands in the other tissues called the acinar tissue. They're very distinctive. They're just kind of scattered around. So good descriptive name. Does that make sense? Okay. If I'm a doctor and I'm an endocrinologist and I'm my age, I'm going to call the islets of Langerhans because that's what I learned. And if you don't know what I'm saying, then you better get on board or go find a job someplace else. Because I'm the doctor and you're not. Unless you're going to be a doctor, and then you can argue with that guy. Does that make sense? If you work in a hospital, you've kind of figured that out probably. You know, doctors here, orderlies here, everybody else sort of in between, correct? So what happens is it behooves us to actually know every name possible. So if it's a name, it's a correct name, and it's in a authentic reference of some kind, not Joe Bob's book, The Barbecue and Body, okay, but Tabor's or Mosby or one of those are a different anatomy book. If we were to count it wrong and you could show it's a real word, we would just give you the point back. And we're going to use a variety of words. And I had a...
Somewhat similar?
What?
Them being like somewhat
No,
similar?
not at all. In fact, we're going to use Langerhans cell for the skin. And I bet you everybody in here uses Langerhans cell because the other name, they put 3-4 words together to create the name of this cell. It's like, why? So all my students use Langerhans cell because it's easier to write. So they aren't necessarily going to be similar at all. In fact, they can be totally different. But I'll give you an example of why this is important. I had a student last term, and she is a online transcriptionist, and she gets stuff from all over the country, and she transcribes doctors' records and notes and stuff, and she runs into some real freaky stuff. And the week before, I was talking about the bones of the hand, and we have a naming system that's fairly common for the bones of the hand, and then we have one that's not quite as common but still used. So I gave them the second naming system and explained kind of where it's used mostly. And sure enough, she got a transcript from somebody back east, and in the hand, they were using the word navicular for one of the carpals in the hand. Well, the navicular is a quite large bone in the tarsals of your foot, but there's also the old language has navicular for the hand. And she said, it was really cool because you just told us about that name. I actually could use it. She said, normally on those things, I have to flag it as some kind of peculiarity, and then they have to go back and look to see if the doctor made a mistake or not when he was doing his dictating and stuff. And so you're going to see a lot of doctors from a lot of places, and you just try to use the best language that you can. And for us, if it's a correct name, it's a correct name. So if something has 4 different names, pick one you like and use it. Just make sure you can recognize the other one when somebody uses it. Does that make sense to everybody? Are we okay? The only other thing that I used to go over here is when we talk about inguinal in the pubis or pubic region, sometimes that gets people a little bit confused. So if you actually see genitalia, and assuming that they've kind of drawn these pictures so they're regionally anatomically correct, and you see pubic hair, that'll be the pubic region. And then basically where our leg and our trunk are coming together, this is going to be our inguinal region. And those are the only two that I think people sort of get confused with. The other thing that I'm going to do is I'm going to take an exception here. And so right here, they're saying acromial for shoulder. This is the acromial process. You can feel it right up here. This is the acromioclavicular joint. And we're going to call this acromial. Are you with me? It used to be, we always talked about this rounded part as anatomically the shoulder. So if you see an arrow going to the rounded part, we're going to call it the shoulder. If you see an arrow right up here, we're going to call this the acromial region, and we're not going to call it the shoulder. Does that make sense? And this should be an easy one then, because you've been calling this the shoulder all of your life. So at least that's one point you get all the time. Are we okay? Questions? All right. So moving on here, what we're doing is we're trying to describe a way that we can talk about the abdominal pelvic region and how we would look at this in terms of where things are located. So this system has been around for a long time. This system you see here is a little newer, but still has been around a fairly long time. And so this one uses quadrants. So quad means 4. So what they did is they just divided the body up into 4 sections. They used the umbilicus as kind of the axis. And so we have a transverse plane, and this would be a what? So sagittal is right in the middle of the A. So if it wasn't in the middle of the A, parasagittal plane. And so they divided into 4 groups, and we just have a right upper quadrant, right lower quadrant, left upper quadrant, left lower quadrant. You have 2 sides. If anything is paired, it always has to be designated left and right. So if you've got an upper on both sides, you have to say right and left upper. This is a good system, except if you say if somebody's got some kind of tumor or mass, and you say, okay, they've got a mass in the upper right quadrant, that's going to be a big incision to figure out exactly where that's at. And it's hard for us to talk that way. And so what happens is this system actually allows us to be more specific. And with all the electronic capability that we have right now, this is really a much more efficient sort of system. So what happens in this case is we've got 9 regions that are here. And so they're going to really help you out. This is the hypochondriac, and this is the hypochondriac, so it's just right and left. And so this is going to be the right lumbar, and this is the left lumbar. And this is going to be the right inguinal, and this will be the left inguinal. And sometimes instead of inguinal, this one we call the iliac. So if you see iliac, that's okay. It's the same thing. And so when we take a look at the middle, we just have the epigastric, the hypogastric, and the umbilical region. And so that makes up our 9 regions that are there. This one is a little bit nicer for us. I was in the ER today with somebody, and when we were finished, the person was going to have to contact their personal physician, and the doctor, the ER doctor said, and even right now, they can already go on their computer and just call up your file, and they'll see all the x-rays that we took today. And it was like, it's so cool, because it's just there. So what can happen with this, if I'm a doctor in Grants Pass, and I see something that looks really weird, and I think I know what it is, but it's really unusual. And it's a condition that maybe you just would see 1 in every 10,000 people, and I've never seen it before. But there's a guy in Maryland who's the world's expert on this. I just put that image and I zip it over to him electronically, and he opens it up on his computer and he looks at it and he sends a message back and he goes, "You're absolutely correct. That's just a classic example of what you're talking about. You're right, it's really rare, and I've attached 14 different protocols to help you deal with it that I found have been really successful. And you didn't have to fly to Maryland to go see the doctor and whatever the condition was, it's worse along the way." And what happens is when you say, I'm sending you this image and I can see at this particular place in this region, on this organ, and then pops it up and looks right where you're talking about, and he doesn't take much time for him. And so he's not likely to say, well, it's not one of my patients, I don't even know where Grants Pass is, why should I deal with this? He goes, well, I can take care of this in just a few minutes. Does that make sense? So really a nice way to be efficient and not waste our time. So these are directional references, and you guys talked about these in lab. So we have medial and lateral. In this case, the reference is the midline. So if 2 structures are being compared, it's the one that's closest to the midline will always be medial. The one that's farthest away is always going to be lateral. And so if we took a look at your right eye and your right ear, which one is lateral? The ear, and so the right eye must be medial. But if we did your right eye and your nose, what happens to the eye? It becomes lateral, and the nose becomes medial. So you could be medial or lateral. It just depends on the context of the comparison. So we're always comparing 2 things. So when we take a look at us, we're bipeds, and so we have a tendency to talk about if it's closer to the head, it's superior. If it's farther away from the head, it's going to be inferior. Now, with a dog or a cat or something like that, because they're quadrupeds, we would also sometimes use the word cephalic and caudal, and we have a few places like that in anatomy, but most of the time we don't use those terms, and we just use superior and inferior. In your lab book, that picture of the dog, it kind of compares all of that. So if we take a look at the front part of this person, that's anterior ventral. On the back, posterior or dorsal. Now, a lot of times those are interchangeable, but sometimes they are not. So you've got to be a little bit careful. So when we take a look at the next term, your spinal cord, you have a structure called the dorsal root, and it also has an enlargement there called the dorsal root ganglion. We don't typically call it the posterior root or the posterior root ganglion. And so dorsal is a much more accurate and correct term for that. But a lot of times they are somewhat interchangeable. Are we okay? And then we have distal and proximal here. So proximal means close to attachment of the limbs of the body. Distal means further away. Could I use proximal and distal if I were doing my chin and mouth? No, because those are pretty much relegated to arms and legs, appendages. There's a couple instances where we kind of violate that rule, and when we get to some other systems, we'll kind of point that out. But other than that, that's our basic rule. So if you take a look at, here's my wrist, and here's my, we'll use normal terms in case you don't know all the others. My elbow or my olecranon, this is the carpal region. So this is the olecranon region. Which one's proximal when I'm comparing these? The elbow, and this would be distal. So here's my carpal region, and here are my phalanges, or my digits. And this one's now, and this is proximal. All right, planes. When we talk about planes, your lab book, it does a really good job showing planes and how they section, and it throws in one more plane that this one doesn't do. So we're going to reference your lab book here also. So we see three planes. This one going across is called a transverse. The older name for this guy is a horizontal plane, and occasionally you're going to still run into that. So just kind of keep that in the back of your mind. It's horizontal plane because it was horizontal. If I cut through this person using this transverse of horizontal plane, it divides the person into superior and inferior portions. Not halves, but portions, because we can cut anywhere, correct? Okay? And when I cut it through here, I'm cutting across the person's body. So this is called a cross section. So when you're looking at slides under the microscope, especially when we're looking at tissues, they'll usually label the cut for you. And it'll say CS for cross section. That means we cut across. In other words, it was long and we went like this right through it. Okay? This plane right here is called a frontal plane. The other word for this guy is a coronal plane. And that's C-O-R-O-N-A-L, coronal. You have a suture. It goes across your skull right here called a coronal suture because it was named for the coronal plane. And so you'll see both of these terms. The coronal or frontal plane will separate you into anterior and posterior portions. And it doesn't have to be perfectly even. You can just cut right through here, depending on what we're doing with our imaging and that kind of stuff. This guy that you see that cuts my left and right is called a sagittal. If it's right down the middle, if it's off the middle, it's parasagittal. Now, a frontal plane and a sagittal plane cuts lengthwise, and those are called longitudinal sections. Okay? They're going to cut the length of something. When you're looking at slides, we're going to be doing tissues here starting next week, and then all the rest of the three terms, we'll look at tissues of organs and organ structures. Always look to see what the section is. So if I'm looking at muscle tissue, and it's a longitudinal section, that picture we saw of skeletal muscle and all those cells were lined up, I would see those cells lined up. But if it's a cross section, what I would see is a big circle, and I would have cut across all the cells, and they're kind of symmetrical, and what I would see was a bunch of circles. because they're looking sort of at the end of a muscle. Does that make sense? So longitudinal and cross-section labels will give you context when you're looking at your tissues. It's also important when we're talking about what we're doing with patients and images. And real quick, the last one is a plane that goes like this. And that's an oblique. And so that section is called an oblique section. So anytime we see something running and it's not transverse or horizontal, we will talk about it being oblique in nature. So you've got two sets of muscles right here, and they're called the obliques. They run this way and this way. Okay, see you guys on Tuesday.